Welcome to the Walton Pi. Today we're going to go through a test review that's going to cover things like implicit differentiation, how to take the derivatives of logarithms, inverse trig functions, a couple problems involving rates of change in physics and stuff. We'll have some related rates problems, some maximum and minimum problems, and then we'll conclude with some other things like that, like figuring out how to graph a function based on different conditions. And then we'll talk about a few other things that might show up on this test. So to get started, let's talk about some implicit differentiation. So first off, let's find dy dx if we are given the following situation. We have tangent of x plus y is equal to secant of xy. We are asked to find dy dx. So, as always, pause the video right now and try and do this on your own. It's not going to help you if you just watch me do it, so pause the video, try and do it on your own, and then once you have a solution, unpause it to see the way that I do it, so that you can see if you messed up somewhere or if you ended up getting the same thing, which would be great, because hopefully you're able to do all of these different problems. So, before I start going, pause the video and try and do this on your own. So the first thing that we're going to be doing is we are going to take the derivative of both sides with respect to x. So implicit differentiation, we don't need to solve for y first. So we're going to take the derivative of this side with respect to x, and that's the same thing as the derivative of this side with respect to x. So to start off, what's the derivative of tangent? Well, that's going to be secant squared, so it'll be secant squared of the inside stuff, x plus y, multiplied by the derivative of the inside. This is the chain rule in action. So the derivative of x with respect to x, well, that's just a 1. But then the derivative of y with respect to x, that's dy dx. Or y prime, if that's the way that you prefer to see it. But that is the derivative of the left-hand side. Now what's the derivative of the right-hand side? Well, first we need the derivative of secant. Well, derivative of secant, that is secant tangent. So it will be secant of stuff times tangent of stuff. But then we have to multiply that by the derivative of the inside. So the derivative of x times y, well, that's going to be a product rule with the chain rule. So derivative of the first, that's a 1 times y, plus the first x times the derivative of the second, dy dx. Our goal now is to try and isolate the dy dx's. So we want to get these two pieces together and by themselves. So that means the first thing we're probably going to need to do is multiply things out. So on the left-hand side, that becomes a secant squared of x plus y plus dy dx times secant squared of x plus y. And that is equal to, on this side, we're going to take the secant times tangent times 1 times y, and then add to that the same thing but times x dy dx. So we get on this side secant of xy, tangent of xy, times y, plus x secant of xy, tangent of xy, times x dy dx. So we've now multiplied everything out, and now we are going to want to get everything that has a dy dx to one side. So let's take this piece and move it to that side, and we will take this piece and move it to that side. Once we do that, we are going to get, we have dy dx times secant squared of x plus y minus dy dx times x secant of xy, tangent of xy is equal to y secant of xy, tangent of xy, minus secant squared of x plus y. Well, what we can then do, because there's a dy dx everywhere here, we can factor the dy dx out to be able to then solve for dy dx. So if we were to do that, we would get dy dx times secant squared of x plus y minus x secant of xy tangent of xy is equal to y secant of xy tangent of xy minus secant squared of x plus y. Now, what we now have is we have dy dx times a whole bunch of stuff that can be all in parentheses. So what we can do is we can do division by all of this stuff. So that'll be divided by secant squared of x plus y minus x secant xy tangent of xy. So this is the derivative of y with respect to x. Let's do another problem like this. So let's say that we have x cubed plus 5y squared equals the square root of x plus 3y times cosine of x minus y. So if we have this, let's find dy dx. Go ahead, pause the video, and try this on your own first. Okay, so we're going to go through the same process we did last time, where we take the derivative of both sides with respect to x. So, derivative of the left-hand side. Well, derivative of x cubed, that's 3x squared. Derivative of 5y squared, that's a 10y times dy dx. And this is coming from the chain rule. The next one is the derivative of the square root of x plus 3y times cosine of x minus y. This is going to be a product rule along with the chain rule. So that's equal to the first times the derivative of the second, so square root of x plus 3y, times derivative of cosine, that's a negative sine of x minus y, times the derivative of the inside, 1 minus dy dx, and then close that parenthesis. So first times the derivative of the second plus the second cosine of x minus y times the derivative of the first. Derivative of the square root of something, that is 1 over 2 times the square root of that stuff, x plus 3y, multiplied by the derivative of the bottom. So that's going to be times a 1 plus 3 dy dx. So we have this, and now we are going to have to isolate this dy dx, this dy dx, and this dy dx. We're going to have to get all of those pieces all together. So let's multiply out the pieces that we need. So first off, let's take this negative sign here, and let's distribute it through to these pieces. So that's a plus, a negative 1, and a plus right there, just to make our distribution a little bit easier. So after we distribute out the multiplication, we get 3x squared plus 10y. I'm going to start using y primes. Y prime is equal to square root of x plus 3y times sine of x minus y times a negative 1 plus square root of x plus 3y sine of x minus y times dy dx, or y prime, plus, we're not done yet, we got cosine of x minus y divided by 2 square root of x plus 3y, and we have a plus 3 cosine of x minus y over 2 square root x plus 3y times y prime. So we have all of those pieces, and now we are going to try and get this y prime, and this y prime to all be on the same side. So since we already have 2 on one of the sides, let's take this piece and move it that way, and we will take every piece that does not have a y prime and move it to this other side. So after we do that, we get 3x squared minus the negative, so that's a plus square root x plus 3y sine of x minus y. And then we have a minus cosine of x minus y divided by 2 square root x plus 3y. And that is equal to, we have a y prime times a whole bunch of different pieces. So we have a y prime times square root of x plus 3y sine of x minus y. We have a plus 3 cosine of x minus y divided by 2 square root of x plus 3y. And then we have a minus 10y, because all of those are multiplied by y prime. Now, to get y prime, we are going to take this entire piece and move it over to the denominator of the other side. So let's just grab that, because I don't feel like trying to rewrite this. So we take all of this, and we are going to move this to the denominator of this. So it's all of that divided by that stuff. And so that is going to be y prime in this case. That is how we would be able to go about and solve that. Now, is that a pretty way to see it? Absolutely not. But that is what the derivative of this function would be. So let's transition from these directly implicit differentiation problems to some common ones that you might see on a test, especially in a multiple choice setting. So, find dy dx for the following. So, first one, y equals inverse sine of x. Second one, y is equal to inverse cosine of x. And then the third one, y is equal to inverse tangent of 2x. So go ahead, pause the video, and try and figure out how would you take the derivatives of each of these different things. Alright, so let's go through some of these together. So for the first one, we will want to rewrite this so that we see a derivative that we can do. Well, remember, y equals inverse sine of x. That's the same thing as saying that sine of y is equal to x. Well, this is then an implicit differentiation problem. So the derivative of this with respect to x, that is going to be, well, derivative of sine, that's cosine. So we got cosine of y times derivative of y is equal to 1. So we get y is equal to 1 over cosine of y. Great. Except for one tiny detail. We were given this problem to find it in terms of x. We currently have it in terms of y. We need to replace that with something to make it in terms of x's. Well, this is where we're going to be coming back to the triangle stuff that we were doing. So if we were to look at the triangle for sine of y equals x. So we have a right triangle, sine of y. That tells us that y is our angle. But then, what's the x tell us? Well, remember the rule for SOHCAHTOA? So that is SOHCAHTOA. This tells us the ratios of the sides that correspond to sine, cosine, and tangent. So sine, that is opposite over hypotenuse. So that means that the ratio of our opposite side to our hypotenuse side has to be x. Well, one choice for that is this to be x and this to be 1, which then tells us, what's this last side? What's that going to be? Well, the Pythagorean theorem allows us to figure that out. So this is the adjacent, so we get that a squared plus the b squared, which in this case is x, that's equal to 1. So a squared is 1 minus x squared. So a is the square root of 1 minus x squared. So we can put that here. And so now, what's cosine of y? Well, cosine, that's adjacent over hypotenuse. That's going to be the square root of 1 minus x squared over 1. So, cosine of y is then the square root of 1 minus x squared. So y prime, whoops, I forgot a prime here. So that means that this y prime is going to be 1 over the square root of 1 minus x squared. So that's how we would be able to find that one. So if you weren't able to figure these out first, pause the video and try and do the second and third ones on your own. Okay, so let's go through and figure out this second one. So first step is going to be similar to the first step we did in problem 1, where we are going to first rewrite this. So y equals inverse cosine of x. That's the same thing as saying cosine of y equals x. Then we're going to take the derivative with respect to x. So a derivative of cosine, that's negative sine times y prime is equal to 1. So that means that y prime is a negative 1 over sine of y. Well, we're going to need to know what is the derivative of, or what is sine of y. So we're going to draw another one of these triangles. This time it's cosine of y, so y is again our angle. But then this time it's adjacent over hypotenuse is x. Because cosine is adjacent over hypotenuse, so that means that it's going to be x and 1 here. So then this side, again, we're going to need to use the Pythagorean theorem to solve it. But we again find that that is going to be the square root of 1 minus x squared. Which means sine is opposite over hypotenuse. So that means that sine of y is the square root of 1 minus x squared. So this time, y prime is negative 1 over the square root of 1 minus x squared. So that's the derivative of inverse cosine of x. So now let's do the last one, which is probably going to be the trickiest of these. So what are we going to do here? Well, we can take the derivative of both sides after we've rewritten it a little bit. So first, rewrite this. So this will become tangent of y is equal to 2x. So then when we take the derivative of both sides, what's the derivative of tangent? Well, that's secant squared. So we got a secant squared of y times y prime is equal to 2. So that means that y prime is going to be 2 divided by secant squared of y, or we can move the secants to the top as cosines. So this is a 2 cosine squared of y. But that still means that we're going to need to know what is cosine. So we're going to draw another triangle. All of these problems, if you haven't drawn a triangle, you probably messed up somewhere. So always draw the triangle. It's very, very helpful to us. So tangent of y, well, y is our angle again. This time tangent, that is opposite over not over hypotenuse, over adjacent. So opposite over adjacent, and that's equal to 2x. So 2x divided by 1, that's one way to get 2x. So now we have to figure out what's our hypotenuse, because we need cosine, so we need adjacent over hypotenuse. Well, Pythagorean theorem says that 1 squared plus 2x squared is equal to our hypotenuse squared. So let's say 1 plus 4x squared equals hypotenuse squared. Our hypotenuse is the square root of 1 plus 4x squared. Square root 1 plus 4x squared. So what's cosine? Well, cosine of y, that's going to be adjacent over hypotenuse, 1 over the square root of 1 plus 4x squared. So squaring that, cosine squared of y, that is a 1 over 1 plus 4x squared. Put this piece together, and we find that y prime is equal to 2 divided by 1 plus 4x squared. And that is going to be how we would take the derivative of this function. Some other functions that we would need to do this with are going to be logarithms. So anytime we have a logarithm, we are going to need to do implicit differentiation on it. So let's find dy dx using implicit differentiation of y equals natural log of x. So if we have this memorized, we know what we should end up with. But if we don't have this memorized, or if we are asked to do this using implicit differentiation, we're going to have to use implicit differentiation. So the first thing we have to do is rewrite this into a way that we can take a derivative directly. Well, y equals natural log of x. We can't do that directly yet, but what we can do is we can rewrite y equals ln of x. That is the same thing as saying that x equals e to the y. Well, this is something that we can take the derivative of. Derivative of this with respect to x, that goes to a 1 equals e to stuff is e to that stuff times the derivative of that stuff. So that means that y prime is 1 over e to the y. But again, we were given this in terms of x, so we need to replace this e to the y with something in terms of x. Well, e to the y is equal to x, so that's why y prime is 1 over x. So let's do the same sort of thing, but where y equals log base 3 of x. Go ahead, pause the video and try and do this one on your own. Okay, so what we can do is we can say that this is the same thing as 3 to the y equals x, which when we take the derivative of this is going to be what? Well, what's the derivative of 3 to the y? Well, if you remember that, great. If you're like me and can't remember it, this is what we're going to have to do. We have to first rewrite this before we can take a derivative. So if we were to rewrite this, we would like this to be e to something, because those are things we know how to take the derivative of. Well, 3 to the y, I don't see how I can get e out of that, but we can always write it as e to the natural log of 3 to the y. But then we can use logarithm rules and pull out the y, so this is e to the y times natural log of 3, and now this is just going to be a chain rule problem. So we get e to the y times natural log of 3 is equal to x. Then when we take the derivative of this with respect to x, derivative of e to stuff, well, that's just going to be e to stuff times the derivative of that stuff. Well, natural log of 3, that's a constant times y, so that'll be that constant times y prime, and that's all equal to 1. So y prime is 1 over e to the y times the natural log of 3 times the natural log of 3. Well, e to the y, e to the y times natural log of 3, well, that's this thing, which is another way of writing e to the natural log of 3 to the y, which is the same thing as 3 to the y, which is just x. So this is 1 over x times natural log of 3. That's what the derivative of that would be. So let's do one last problem involving logarithms. So find y prime if y is equal to the natural log of x squared plus 5x plus 6. How would we take that derivative? Go ahead, pause the video and try and do this on your own. Okay, so there's a couple ways we could do this. We could take the derivative directly, or we could simplify first. So let's do it directly first. Well, y prime is going to be the derivative of the natural log. Well, we found that is 1 over the stuff that's inside the natural log times the derivative of that. So that's going to be a 1 over x plus 5x plus 6 multiplied by the derivative of the inside, 2x plus 5. Great. That is the derivative of y. But the other way is we could simplify first. Well, y equals the natural log of x squared plus 5x plus 6. That's the same thing as y equals the natural log of x plus 2 times x plus 3. Because x squared plus 5x plus 6 factors that way. Well, now we have logarithm of two things multiplied together. So this is natural log of x plus 2 plus the natural log of x plus 3. And then we can take the derivative of this. Well, derivative of natural log of x plus 2, well, that's going to be a 1 over x plus 2 times the derivative of x plus 2, which is 1. And we have plus 1 over x plus 3, because that's the derivative of natural log of x plus 3. It turns out that these two numbers, or not numbers, these two functions are equivalent. If we were to multiply 1 over x plus 2 and 1 over x plus 3 by x plus 2 over x plus 2 and x plus 3 over x plus 3 to get common denominators, we would end up with the equation from number 1. Both of them are perfectly valid answers. It's just sometimes one is a lot easier to the other. So sometimes it might be better to simplify first before you take a derivative. Alright, let's go through some related rate problems. So let's suppose that you are inflating a pool floaty, and this pool floaty is in the shape of a donut. So we got this nice little donut shape, and we are inflating this balloon. Now, one of the challenges with a donut is, first off, what's the volume of a donut? So let's draw a little bit better of a donut. So we have a donut that is going to be like this. So we got this, here's our center. Now there's two different radii that show up in a donut. So we have this inside radius, which we are going to call little r, and we have this big radius that is 3r, where this big radius goes until it reaches the center of the little circle here. Now, we need to know what the volume of this is, and I'm just going to give this to you. So the volume is going to be equal to pi little r squared times 2 pi big R. That's going to be the volume of the donut. Now, if we have this, and we know what this is, let's say that we are also told that the big radius, big R, is equal to 3 times the little r. So that's what I was labeling up here. If we have this, we might ask ourselves, what is the rate that the height of the floaty is increasing after 16 minutes if we know that we are blowing in, so we have a pump. Let's see, where can I put this? There we go. Put it over here. Where we are pumping pi squared cubic feet per minute of air into this tube. Now, we're going to have to stretch exactly how floaties inflate just a little bit. So instead of this floaty like starting completely flat and then rising up, we are imagining that this donut starts as a really, really small donut and then is increasing and every part of the donut is stretching out. So kind of like a balloon rather than an actual floaty. So we have a donut-shaped balloon. Now, what's the rate that the height of the floaty is increasing? How are we going to find that? Well, height, that's our... We need to somehow connect the volume to the height. So we know that we have pi squared cubic feet per minute. So that means that we know that dv dt, the rate that the volume changes with respect to time, is pi squared. and we are trying to find dh dt. Now, the problem is in our equation for volume, there's no height anywhere. But what's the height of the floaty? Well, the height of the floaty is this distance right here. So that means that h is equal to 2r, which means that dh dt is equal to 2 dr dt. So we are going to need to figure out what's dr dt to then figure out what's dh dt. So let's go through and do that. So we know that volume, let's rewrite this a little bit by substituting what big R is. Volume is pi little r squared times 2 pi times 3 little r. So that means that volume is 3 times 2 is 6. So we have a 6 pi squared r cubed. That is what the volume is going to be at any given radius. Now, we are going to take the derivative of everything with respect to t. So we get a dv dt is equal to 6 pi r, that's a constant, so that'll stick around. 6 pi squared, that's the constant, so that sticks around. Multiplied by the derivative of r cubed, well, that's a 3r squared dr dt. Or an 18 pi squared r squared dr dt. So that's going to be what dv dt is. And now we're going to be able to connect a little bit of this. Because we know that dv dt, let's leave a little bit of this still around. We know that dv dt, this is pi squared. So we got pi squared is equal to 18 pi squared r squared dr dt. The pi squareds can cancel, so we are left with dr dt is equal to 1 over 18 r squared. So dh dt, that's 2 times dr dt. Remember, we found that a little bit earlier. So because of that, that means that this is going to be 2 over 18r squared, or 1 over 9r squared. That is what dh dt is. Well, that's great, but we are wanting this after 16 minutes. So we need to know what is the volume after 16 minutes. Well, volume after 16 minutes, that is going to be equal to 16 times the pi squared cubic feet per minute. So that means there are 16 pi squared cubic feet of air inside the floaty at 16 minutes, and we can solve for what R would be. So that is equal to 6 pi squared r cubed. The pi squareds can cancel, so we get 16 equals 6r cubed. So r cubed is 16 over 6, that is 8 over 3. So that means that r is going to be 2 over the cube root of 3. So we can then plug that in. So that means that we know that dh dt is going to be equal to 1 over 9 times 2 over the cube root of 3 squared. So that's going to be a 1 over 9 times 4 over the cube root of 9. So that's going to be the cube root of 9 over 9 times 4. That, how fast the height of the floaty is increasing at 16 minutes. So, we bring that all back. We find dh dt is equal to the cube root of 9 over 36 feet per minute. And that is what our answer for this one would be. Let's make it so that we can see all of this. There we go. Let's do one more problem. And again, as always, try and do this one on your own before you watch me go through and do it. So, this time, we are going to be looking at an equation that measures static in a phone line depending on how many people are calling through the same cell tower. So, the amount of static so let's say it is S in the number of crackles that in your phone call. So when you're on a phone call, oftentimes there's little bits of crackles and popping. So the amount of crackle and pop that's going to be in the phone call, we are going to say that this follows this equation. And this time we are going to say that N is the number of calls at the same time. So that's what N is going to represent. So static is equal to 12 plus N squared log base 10 of N divided by 13 plus N. So as we get more and more phone calls, there's going to be more and more cracklage, if that's a word, in our phone line. Now, this particular problem is going to say that at 4 p.m., high school lets out and there are currently 1,000 people on the phone. With 20 new calls each minute. Okay, so the question is, how fast is S changing in static cracklage per minute? That's what we are trying to figure out and measure. So pause the video, try and do this one on your own, and then we will come together and try and do this and see how we would go about doing this problem. Alright, so let's go through this together. So we know how many new calls there are at any given time. So this 20 new phone calls each minute, that the NDT, so the rate that the number of calls changes, is equal to positive 20. We are gaining 20 new calls each minute. So the question is, how fast is S changing? Well, that means we need to find what is ds dt. Well, we have an equation for S. So that means we can say that ds dt is equal to the derivative of that function. Well, how do we find the derivative of that? Well, that is going to be, you guessed it, the quotient rule. So we got low d high. So we got a 13 plus n times the derivative of the top, derivative of 12, that's 0, but the derivative of n squared log base 10 of n, well, that is going to be a rule. So the derivative of n squared, that's a 2n, so we have a 2n log base 10 of n, plus n squared times the derivative of log base 10 of n, well, that's going to be 1 over n times what? Well, that's going to be times natural log of 10. Right? Because what we can do, if you don't remember that, rewrite log base 10 of n. This is natural log of n over natural log of 10. Oh, which means that when we take the derivative, it's going to, instead of being times the natural log of 10, it's going to be divided by the natural log of 10. Times 1 over natural log of 10. So we have that. So that's going to be that top piece. So low d high, oh wait, we still have more we have to do. That's low d high, we still have minus high 12 plus n squared log base 10 of n times the derivative of the bottom, that's just a 1, all over the bottom squared. Now, here's the thing. Is what I wrote down correct? Not quite. See, anytime we take the derivative of n, that's going to be having a dn dt come out. So where did we do that? Well, right here, 2n, that needs a dn dt with it. So we got dn dt right there. Well, here we took the derivative of this stuff. That means that we need a dn dt there. So let's actually just put the dn dt outside of this entire parenthesis, because all of those had a dn dt on them. dn dt. And then this one, the 12 plus n squared log base 10 of n, well, that was just the top times the derivative of the bottom. Well, derivative of the bottom is not actually 1. It's a dn dt. So we actually had a dn dt everywhere in this problem. So now what we can do is we know what is n, it's 1,000, and what is dn dt? It's 20. So that means we can say that ds dt is equal to 13 plus 1,000 times 2,000 log base 10 of 1,000, well, that's 3, plus 1,000 squared times 1 over 1,000, well, squared and that will cancel, times 1 over natural log of 10. Whoops, forgot the minus. So all of that is times dn dt, 20, minus, we got 12 plus 1,000 squared log base 10 of 1,000, that's 3, times 20, all over 13 plus 1,000, so that's 1,013 squared. And whatever that number is, that is going to be what ds dt is. So we can do a little bit of simplification, not a ton. Let's just evaluate what some of these numbers are. That's going to be equal to 1,013 times 6,000 plus 1,000 over the natural log of 10 times 20. Let's see, we got minus 3 times 1,000, that's 3,012 times 20, all over 1013 squared. So whatever that is, that's going to be how fast the amount of cracklage, changes. So let's go ahead and figure out what that is approximately. So I'm just going to pull out my calculator and type this in and see what that would be about. So we got, let's see, 1013 times 6,000 plus 1,000 divided by, see, we got the natural log of 10. Let's see, and then that's times 20 minus 3,012 times 20. And we divide all of that by 1013 squared. And we get that is approximately 68.56. So that means we are increasing at about 68.56 crackles per minute, which is alright. Like, that's about a crackle a minute, or a crackle a second. That's not terrible, but it's not great at the same time. So we might need to switch cell carriers at that time. Alright, let's start talking about some local maximums and local minimums. So let's say that we were given a graph like this on our test, and we are asked to find all the local minimums and local maximums, as well as the absolute minimums and absolute maximums. So local minimums, depending on your textbook definition, might be allowed to include endpoints, might not be able to include endpoints. So, for example, this region right here, this point right there, if we are allowing endpoints to be local minimums and local maximums, then this would be included as a local maximum because it is bigger than everything else around it. So we might say that x equals 0 might be 1. So 0, 0 is a potential local maximum if you are allowing endpoints to be included. I personally like that definition a little bit more, but it is up to your textbook. So go back through and check to see which one it is. I believe the common textbook for most calculus classes at universities say that endpoints are not allowed to be local maximums. So I will not be including this one because I don't think it is going to be the commonly accepted definition. But go back into your textbook and check to see which one is which. So that is not going to be considered a local maximum because of that. Now let's go through and figure out where are some actual local maximums and local minimums. Well, one of them is going to be right here at the very bottom of this. So this is a local minimum, so that's going to be the point 1, negative 1. And then we have a local maximum here at about 3, 1. But then we have another local minimum right here at about 4 and 1/2. So 4, 1/2. Now, the question is, what is this? Is that going to be a local maximum? Well, it's not including the endpoint of that piece, so that can't be a local maximum because it's not going all the way up. And also, if we were to draw a little region around it, we see that we actually have a local minimum here. Because this point right here at 6, right down here, that is farther down than anywhere else on either side. So that means we have a local minimum right there at about 6, negative 3. So we have another one right there. Then we have a local maximum right about here at about 7, minus 1. Then we have another local minimum here at about 8, negative 2. I'm running out of room there. 8 and negative 2, so there's another local minimum. And then we don't have anything else because this region right here, that's going up and up, but it looks like it's going to be horizontally tangent to the line y equals 0. So that means we're not going to end up with any more local minimums or local maximums there. So now that we have those, let's start talking about the absolute maximums and absolute minimums. The absolute minimum is really easy to spot. It's just this point way down here. So the absolute minimum is 0.6, negative 3. Nothing else on this function that gets below that. Now the question is there an absolute maximum? Well, we might think, well, it's going to be up here at like height 3. But the problem is if we keep zooming in on that, so if we zoom in, we'd get this region. But then if we zoom in on just this section here, we'd get this. So no matter how much we zoom in, there isn't a top point. So in this example, it turns out that the absolute maximum does not exist. There isn't one. And that's completely valid. That is something that is completely fine having in your problem. Alright, now that we've done some absolute maximums and minimums and stuff by looking at a graph, let's do some of those same things, but this time from a function. So let's say that we have f of x is equal to 3x to the 4th minus 4x cubed minus 72x plus 17. And we are trying to find the absolute maximum and the absolute minimum on the interval -5 to 5. So if we're trying to figure this out, what are we going to need to do? Well, we can use the extreme value theorem to help us out. So the extreme value theorem, if you don't remember this, what this says is it says that if you have a closed interval, kind of like this, so closed interval from -5 to 5, and our function f is continuous, then that means that there is going to be an absolute maximum and an absolute minimum somewhere. And it'll either happen at the endpoints or at the critical points. So our critical points, let's try and figure out what those are. So we need to take the derivative. And so the derivative of this is going to be 12x cubed minus 12x squared minus 72, which is able to have a 12 pulled out. So we get 12 times x cubed minus x squared minus 6. Now we have to just find what are the zeros of x cubed minus x squared minus 6. Well, if we go through and try and figure some of those out, let's try and guess what some of them might be. So 1, that's not going to work because 1 minus 6, that's negative 6. 2, let's see, 8 minus 4 minus 6, that didn't work. I'm wondering if this one even has any nice solutions. Let's tweak this just a little bit and make it so it is 72x squared, just so that it's able to be done. So then the derivative is not going to be minus 72, but is instead going to be minus 144x, which again we can still pull out a 12 from everything. In fact, we can pull a 12x out of everything. And we are left with x squared minus x minus 12. And then this factors a lot nicer. So 12x times x minus 4 times x plus 3. So this means that we have 3 critical points. So our critical points, these are 0, 4, and negative 3, because those are the zeros of our derivative. And then we can figure out, are any of these local minimums or local maximums? But if all we care about is the absolute minimum and absolute maximum, we just have to plug these into our function. So we just need to know what is f of 0, f of 4, f of negative 3, and then the extreme value theorem says also look at the endpoints. So f of negative 5 and f of positive 5, and we just need to evaluate what all of these are. So f of 0, that's the easiest one, so that's just going to be 17. Let's go through some of the others. I'm going to grab my calculator and quickly compute these. Alright, so after using my calculator to figure out what these different ones are, we found that f of 0 is 17, f of 4 is negative 623, f of negative 3 is negative 280, f of negative 5 is 592, and then f of positive 5 is negative 408. So if we are looking for the absolute maximums and absolute minimums, we just go through and find which one's the biggest. This one's the biggest. And then which one is the smallest? Well, this one's going to be the smallest, so that means that our absolute maximum is going to be f of negative 5, which is 592. And our absolute minimum is f of 4, which is negative 623. And so that's how we would be able to go about doing this if we were given a function instead. So now let's talk about doing the local minimums and local maximums from a function, because this is going to be slightly different. So let's clear the canvas. Let's say that we have the function g of x is equal to sine of x times e to the x. And we are trying to find all local maxima and minima on the interval -4 to 4. Now, we could also go through and figure out where are the absolute maximums and absolute minimums, but let's only care about the local maxima and minima. So, if we were to go through and do this, what would we need to do? Well, there's a couple choices. We can do either the first derivative test or the second derivative test. Let's just do the first derivative first, because we're going to need to take the derivative regardless of which method we want to use. So, if we look at the first derivative, using the product rule, we find that the derivative of this is going to be sine x e to the x plus cosine of x e to the x, which is equal to sine x plus cosine of x all times e to the x. Now, we want to find where are our critical points. And remember, our critical points happen where g prime of x is equal to 0. These are how we can find those different things that might be local minima or local maxima. Now, if we want to set this equal to 0, that means that we have sine x plus cosine x times e to the x has to be 0, but e to the x, that is never 0. So this tells us that we need sine x plus cosine x to be equal to 0, or in other words, sine x to be negative cosine of x. And if we divide both sides by cosine of x, that means that tangent of x is equal to -1. Well, we know where tangent of x is -1. That happens at x equals negative pi over 4. Now the question is, where else does that happen? So, on our unit circle, remember, we have negative pi fourths, that's this angle right here. Well, other spots where that's going to happen is over here, and then any time we have gone around the circle 2 pi. So that means that all the x values, so our critical points, these are all going to be of the form negative pi fourths plus pi times some integer n. So plus 1 pi, plus 2 pi, plus 3 pi, minus 1 pi, minus 2 pi, all of those are valid answers. So now we just need to know which of these are between -4 and 4. Well, if we just start listing them, one is going to be negative 5 pi over 4. Well, what is 5 pi over 4? Well, 5 pi, that's about 15 divided by 4. That is still going to be less than -4. Let me just make sure of that real quick by doing that calculation real quickly. Yeah, so this is about -3.927 and then some change. That one's inside our region. Then we have pi fourths, or negative pi fourths, 3 pi fourths. But then if we add any more, that's going to be outside of our range. So these are the only places where we might have a local maximum or a local minimum. So now we just have to figure out, are they going to be positive or negative? Well, we can now either do the first derivative test or the second derivative test. So let's write down g of x one more time so we have it. Sine x e to the x. Let's go through the different tests. So our first derivative test, we are going to need a number line. So we got, here's negative 5 pi over 4, here's negative pi over 4, here's 3 pi over 4, and then we have our endpoints at 4 and -4. So these are going to be the regions that we care about. So we just need to figure out, is the first derivative positive or negative in each of these intervals? So remember, g prime of x, that is sine x plus cosine x times e to the x. Now, we only care about the sign, so the fact that this is always positive, no matter what, that means we only really have to look at what's the sign of sine x plus cosine x. Well, let's just plug in some easy numbers. So an easy number to plug in between negative pi fourths and 3 pi fourths is 0. Well, sine of 0, that's going to be 0, and cosine of x, well, cosine of 0, that's 1. So this is going to be positive, because 0 plus 1 times some positive thing, that's going to be positive. But if we were to plug in something bigger than 3 pi over 4, that's easy to calculate, such as pi, well, if we plug in pi, sine of pi, well, okay, that's again going to be 0, but cosine of pi, that's negative 1. So we have a negative times a positive. And then if we were to plug in something in this range, like negative pi, well, that's going to be negative. And if we continue this pattern, we would find that this is going to be positive. So where do we have local maximums? Well, a maximum, that's where it increases and then decreases. So we have a maximum here and here. So we have local maximums. I didn't have a spot to write it. So we have local maximums at, oh, that is very bad spelling on my part. We have local max at x equals 3 pi over 4 and negative 5 pi over 4. And we could figure out what those points are. So the points would be negative 5 pi over 4, comma, f of negative 5 pi over 4, whatever that is. And then our other one would be 3 pi over 4, f of 3 pi over 4. Now if you had this on a test, I would recommend actually plugging this into your function. So take this and actually plug it in to figure out what number that is. But we know what our function is. Oh, they're f's, not g's. So those should be g. But yeah, so you would just take those and plug it in. So you'd have sine of negative 5 pi over 4 plus cosine, or into the original function. So they'd just be sine of negative 5 pi over 4 times e to the negative 5 pi over 4. I don't know what that number is, but that's what we would write down. And then similarly, we would have a local minimum. Those would be where x is going to be decreasing and then increasing. So that's only going to be at negative pi over 4. So the point would be negative pi over 4 f of negative pi over 4. And that's how you would be able to do this using the first derivative test. Now, if we wanted to do this using the second derivative test, well, that's where we're going to need to use the second derivative. Well, I guess that's kind of in the name. So we'll need to find what's the second derivative of our function. So we have g prime of x was sine x plus cosine x e to the x. So g double prime of x, using the product rule, is going to be first times the derivative of the second, sine x plus cosine x e to the x, plus the second times the derivative of the first. Well, derivative of sine, that's cosine. Derivative of cosine, that's a negative sine. This can simplify quite a bit, actually. So cosines combine, the sines cancel, so this is actually just 2 cosine x e to the x. I did that right, correct? Let's see, first times the derivative of the second, plus the second times the derivative of the first. Yep. Okay, so that's what the derivative is. So now what we would do is, for the second derivative test, we just need to plug in our critical points into our second derivative. So we got g double prime of negative 5 pi over 4. That's going to be 2 cosine of negative 5 pi over 4 e to the negative 5 pi over 4. Well, let's see. This is positive. Cosine of negative 5 pi over 4, let's look on a unit circle. Negative 5 pi fourths. So that is going to this angle right here. That means that the cosine value is negative. So this is all going to be less than 0. And remember, if the second derivative is negative, that means you're feeling kind of down. Whenever you're negative feeling, you're making a frowning face. Remember, this is concave down, which means that this is going to be a maximum. So this is a max, which is the same thing that we found before. And if we were to do the second derivative at negative pi fourths, we would find that this is positive, so it's concave up. So this one is going to be a max. And then we would do the same thing where we'd say g double prime of 3 pi fourths. We'd find that was also going to be negative, so it would be a local maximum. Sorry, I wrote the wrong thing right here. If it's concave up, that means it's a minimum. Okay, so now that we've done those, let's do one more problem together where we're going to go through both of these tests again. So, this time we got f of x is equal to 5 fourths x to the fourth plus 5 thirds x cubed minus 15x squared plus 12. We want to find all local minimums and maximums of this function. And we are not going to give us any restriction on our domain. Go ahead, try and figure this out on your own, and then unpause the video when you are ready. Alright, so let's start by doing it by the first derivative test. So, if we are trying to solve this using the first derivative test, let's go through and find out what's the first derivative. Well, f prime of x, this is just a polynomial, so we take the derivative and we get 5x cubed plus 5x squared minus 30x. And then when we factor this, we get a 5x times x squared plus x minus 6. So that's a 5x times x plus 3 times x minus 2. So, first thing, we have critical points of 0, -3, and +2. So, draw our number line, put those on our line, so we got -3, 0, and 2. We now need to figure out what is the sign of the first derivative. So f prime of x. So let's just pick some values that are bigger, that are in between each of these different regions. So maybe we'll pick -4, -2, 1, and 3. So let's go through and figure out what are those different values. So f prime at -4, f prime at -2, f prime of 1, f prime of 3. Well, if we plug in -4, let's plug them into this last one because that's the easiest to evaluate. So we got a -20, -4 plus 3, that's a -1, -4 minus 2, that's -6. And all we care about is the sign. So we have negative times negative times negative, that's 3 negatives, so that one is negative. So right here, the sign is negative. But then if we look at f prime at -2, if we plug in -2, we get -10 times 1 times -4. 2 negatives, that makes a positive, so it's a positive here. F prime of 1, that's going to be 5 times 4 times -1, that's negative. And then f prime at 3, well, that's going to be 15 times 6 times 1, that's positive, so it's going to be a plus here. Now that we have all of these, remember, we have to check these every single time if we want to do the first derivative test. It will not always alternate. We have to go through and check every single one of these things. But now that we know that we have a plus, it goes minus, plus, minus, plus, now we can identify what the different points are. So at -3, because it decreases and then increases, this one's a local minimum. At 0, it increases then decreases, so that's a maximum. And then at 2, it decreases and then increases, so that's a minimum. And so that tells us that we have local minimums at -3 and +2, and a local maximum at 0. Now, let's do the same thing using the second derivative test. So the second derivative test, we still need to know what our critical points are going to be. So if we look at the second derivative test, first thing we need are critical points. So critical points are -3, 0, and 2. We need our first derivative so that we can take its derivative. So it was, let's go to the original derivative, because that's easier to take the derivative of, plus 5x squared minus 30x. Now, if we take the derivative of this, we can find that the second derivative is 15x squared plus 10x minus 30. So we can factor out a 5 from everything. 5 times 3x squared plus 2x minus 6. And we don't have to factor this, actually. We don't need to find where the zeros of this are. If we needed to find the points of inflection, those we would need to take the set this equal to 0 and solve, but all we care about are the local minimums and maximums. So we just need to know what is f double prime at our different points. So f double prime at -3, f double prime at 0, and f double prime at 2. Well, f double prime of -3, let's see, so that's going to be 5 times 3 times 9, that's 27, minus 6 minus 6, that's positive. F double prime at 0, that's going to just be -30, that's negative. F double prime of 2, well, that's going to be 5 times, we got 12 plus 4 minus 6, that's positive. So we just need to identify if the second derivative is positive, what does that mean? Well, if the second derivative is positive, you're probably going to smile. If you're smiling, that's going to be a minimum. And if the second derivative is negative, well, you're probably going to be frowning, and that means it's a maximum. That's one way that you can approach it. So if it's going up, this is concave up. If it's going down, that's concave down. So that's one way that you can remember it. So that means that at -3, because it is positive, it's smiling, so it's a minimum. 2 is also going to be a minimum, but then 0 is going to be a maximum because it is concave down at that point. Alright, let's do some word problems. So let's suppose that you were writing an English paper and got really bored, because we all know that we much prefer doing math homework to writing English papers. And let's say that you were deciding to practice your math while you were delaying working on your English paper, and you decided to figure out how many words do I fit on an average line. And you found that the number of words that fit in one line when in your English paper follows w of x, where w represents the number of words, is equal to 10 times 1/2 plus e to the 2 minus x over 12. Because we all know that is something that we easily find when we are measuring the number of words per line, where x is the font size, and we also found that the height of one line in pixels was 8 plus 2x, where again x is representing the font size. So we know that our average paragraph in our paper, 90 words, let's find two things. So first, the height of the paragraph when the font is 24 point, and b, the rate that the height of an average paragraph is increasing per day if we are increasing the font size by 3 points per day to try and get the paper long enough to turn in, because it's much easier to just increase the font size than to actually write more words. So let's go through and figure out these two different things. So the first one is, what's the height of the paragraph when the font is 24 points? Well, what does this mean? Well, we know that the entire paragraph has 90 words, but not all of those words are going to fit in one line. So first, we're going to need to know what's the number of lines, and then second, we need to know how tall are each of those lines. So what we can do is we can find an equation that says the height of the paragraph, so h of x, where this is the height of the entire paragraph, this is equal to the number of lines, so let's say that that is L, so this is the number of lines, times the height of one line, h of x. So we need to figure out how many lines are there going to be in a paragraph. Well, we know that we can fit a certain number of words per line, and then that's going to be able to get us to how many lines there's going to be. So the number of lines is going to be 90 divided by how many words we can fit in one line. So that's 90 divided by w of x. So that means that our entire height function is going to be 90 times our height divided by the number of words we can fit per line. And this is going to give us the height of the paragraph. So when the font is 24, we need to figure out what's the height. So h of 24, well, that's going to be 90 times little h of 24 divided by the width, or the number of words when there are 24 point font. Well, height of 24, we can come over here and say, well, height of 24, that's going to be 8 plus 2 times 24, that's 8 plus 48, so that's 56. This is 90 times 56 divided by the number of words when there are 24 point font. And when we plug 24 into the width, we get 10 times 1/2 plus e to the 2 minus 2. So that's 10 times 1/2 plus 1. So that's 10 times 1.5, so that's 15. Well, 90 over 15, those divide nicely. So that means that the top is a 6. So the height at 24 is 6 times 56, or 336 pixels. So that is how tall this paragraph is going to be. So the height of the paragraph when the font is 24 point, that is 336 pixels. Let's now do part B. Well, we need to figure out what's the rate that the height of a paragraph is increasing. So that means we need to know what's the derivative of our height function of the paragraph. So we need to find what is h prime of x. Well, h prime of x, this is going to be a quotient rule problem. So we have low d high, so that'll be a w of x times the derivative of the top, so 90 times h prime of x, minus high, 90 times h of x, times the derivative of the bottom, w prime of x, all over w of x squared. And now we can plug these different pieces in. We know what w of x is, we know what h of x is, so what's h prime? Well, h prime of x, that's going to just be 2. The derivative of 8 plus 2x, that's 2. Now, what's the derivative of the width function? This is going to be a little bit trickier. Well, the derivative of this, first we might want to break up the width function into a couple pieces. We might want to say, here, let's get ourselves a little bit of room. So we got width of x, that is, let's multiply the 10 all the way through. So that's going to be a 5 plus 10e to the 2 minus x over 12. Now if we need to take the derivative of that, w prime of x, well, the derivative of 5, that's 0, but then the derivative of 10e to the stuff, well, this is where we're going to need to use the chain rule. So that's going to be 10e to the stuff multiplied by the derivative of that stuff. Well, derivative of 2 minus x over 12, well, that's a negative 1 over 12. So w prime of x is negative 10 over 12 e to the 2 minus x over 12. And this is what we're going to plug in where we have our w prime of x. So let's move this out of our way a little bit. So now we can plug in all the different pieces we know. So we know that h prime of x is going to be our width, 5 plus 10 e to the 2 minus x over 12 times 90 times h prime was 2 minus 90 h of x, 8 plus 2x, times our derivative of our width. Well, that's this entire piece. So negative 10 over 12, so that's a plus, times, we got 10 over 12e to the 2 minus x over 12, all over w of x squared, all over 5 plus 10 e to the 2 minus x over 12 squared. Now, we don't need to simplify this, we just need to know what is this when x is 24. Because that is what we are increasing at a specific time. We are increasing the font size 3 points per day. Now, each of these has a dx dt in it, because this 3 points per day, that's telling us how fast is x increasing. So, if we were to fix those pieces in here, we'd have h prime of x dx dt right there, and a dx dt right here. So the entire thing has a dx dt at the end, so let's just stick that right here. So, going through and plugging in the different values we get, we find that h prime at 24 is going to be, we got 5 plus 10 e to the 0, so that's a 15, times 180, 9 times 2 is 180, plus 90 times 8 plus 2x, let's see, 8 plus 2x, 8 plus 48, that's 56, times 10 over 12 times e to the 0, that's times a 1, all over, let's see, 5 plus 10 e to the 0, that's all over 15 squared, multiplied by dx dt. Well, dx dt is 3, and so now we just have to simplify whatever this is. So, going through and simplifying a little bit more, we find that, let's see, 15 times 180, I feel like there's a lot of 15s that we can be able to cancel. So let's look at 10 over 12 first. So 10 over 12, that's the same thing as 5 over 6. So that is the same as 5 over 6. So 90 divided by 6, that's 15. So we have a 15 there. And then what we have left on the top is we have a 15 over 15. So that means a 15 will cancel from everything. And then we have 180 plus 15 times 56 over 15. So let's write that down. 180 plus 15 times 56 over 15. Well, 180, that's divisible by 15. So we can rewrite 180. Let's see, 15 times 2 is 30, and then 30 times 6 is 180. So 180 over 15, that's 15 times 12. So we have 15 times 12. All of those 15s now cancel. Oh, we forgot to distribute the 3 onto this one. So there's a 3 times this one as well. So that's 36 plus 56. So that is 80 plus 12, so that's 92. So it is increasing 92 pixels per day. That is how fast the height of the paragraph is increasing per day if we are increasing the font size 3 pixels per day, or 3 point per day. Now this makes sense, because if we increase the font size by 3 points per day, that means that our height per line is increasing by 6, and then the number of lines, well, we found that at 24, there were going to be, let's see, 90 divided by 15, so there's about 6 lines, and all of this is making sense. This is about the number that we would expect. So let's now do the second problem that I have prepared. So we have a problem involving Charlie Bucket. So, Charlie Bucket is making rock candy by leaving a string inside water with a lot of sugar dissolved inside of it. Every day, about 16 grams of sugar is crystallizing onto the string. But Charlie, with a little bit of help from Wonka, has decided to get the candy to crystallize into a perfect rectangular prism where the height is always 5 centimeters and the length and width always form a square. So if Charlie started making this candy at the beginning of Monday, how fast is the width of the candy increasing at the very end of Thursday? And if you need it, the density of sugar is 1.6 grams per cubic centimeter. Let's go through and try and figure this out. And yes, I do just realize that this needs an n in there. So it's okay. It's per cubic centimeter, whatever that is, but it's supposed to be centimeter. So let's go through and try and figure out how we would do this. Go ahead, pause the video, and try it on your own first. Alright. The first way that I would do this is I would start to draw a picture of what we are trying to do. So we have a candy that is crystallizing in a perfect rectangular prism where the height is always 5 centimeters and the length and width always form a square. So that gives us quite a bit of information to be able to start to draw a picture. So we know that it's going to be something like this, where the height is always 5, and we know that the base is always the same, so x and x. So what we can then do is we can try and figure out how can we use this to help us figure out some of this problem. Well, we are trying to figure out what are the different things that are connected to this. Well, one of those is the fact that we have 16 grams of sugar is crystallizing onto the string every day. So this actually tells us what's the rate that the volume is changing. It's changing at a positive 16 grams. Are grams a unit of volume? No, like grams are a unit of mass, so we need to figure out what's the volume. Well, that's what this density piece down here at the end is telling us. The density is 1.6 grams per cubic centimeter, so that means this is actually, change in volume is 1.6 grams divided by 1.6 grams per cubic centimeter to give us 10 cubic centimeters. So that's how fast it is changing. It's 10 cubic centimeters per day. So let's try and connect this to what we know. Because we know that this is going to be a representation of the volume. So we know that the volume of the sugar is going to be 5 times x times x. So the volume is 5x squared. But what are we trying to find? We're not trying to find the volume at the end of Thursday, because that would just be how many cubic centimeters were we adding, and then how many days did we add it. No, we're trying to find this. We're trying to find how fast is the width of the candy increasing at the end of Thursday. So the width, that's this thing down here. That's the x that we're trying to find. So we need to find what is dx dt. That's what we don't know. So let's go through and try and figure that out. Well, volume is 5x squared, so if we just take the derivative of everything with respect to t, we get that dv dt is equal to 10x times dx dt. Well, dv dt, that's 10, so we can plug in the things we know. So we get 10 equals 10x dx dt. So dx dt is equal to 1 over x. Well, that was a nice number. That's a nice thing to be able to find. But the challenge with that is, what's x? What is x at the end of Thursday? Well, that's where we come back to our volume equation. We know how many days it's been growing. It grew on Monday, Tuesday, Wednesday, and Thursday. So that's 4 days. So that means we know that the volume is 4 times the number of cubic centimeters it gains per day. So that's going to be 40. So 40 is 5x squared. Divide 40 by 5 and we get 8. We get 8 equals x squared. So x is the square root of 8, which is 2 times the square root of 2. We can take that and put it into this to find that dx dt is going to be 1 over the square root of 8. And what is this? This is centimeters per day. So there we go. We were able to solve this problem. Even though they didn't give us a picture, they just gave us this big word problem, we were able to go through and figure it out by ourselves. Alright, let's do some problems that involve the mean value theorem. So to start off, let's first ask ourselves, is there a point C in the interval from -4 to 2 where we can find that the derivative of f at c is equal to -3 over 128 if f of x is equal to x plus 2 to the -3. So let's try and figure out if the mean value theorem is able to help us do anything with this. So let's first off start to see what are the conditions that need to be met in order for the mean value theorem to apply. So remember, the mean value theorem has a couple conditions. First, we need to have f of x be continuous on the interval a to b. Secondly, we need f prime of x to exist on the open interval a to b. And then we can be able to use the mean value theorem, which says that f prime at c is equal to f of b minus f of a over b minus a for some c in the interval a to b. So, is there going to be a point where f prime of c is equal to negative 3 over 128? Well, let's just take the derivative and see if anything exists. So, let's move the mean value theorem down a little bit. Let's look at what is f prime of x. Well, the derivative of that is going to be negative 3 x plus 2 to the negative 4 times the derivative of the x, which is 1. So this is negative 3 over x plus 2 to the 4th. And we want to see, is this equal to negative 3 over 128? Well, this means that we need x plus 2 to the 4th to be equal to 128, which, let's figure out the power of 2 that is. So that's 2, 4, 8, 16, 32, 64, 128. That is 2 to the 7th. So we could go through and figure this out. So that means that, let's see, so 2 to the 7th doesn't divide 4 nicely. 2, 4, 8, 16, 32, 64, 128. Yeah, it is 7. So that means that we get x plus 2 is going to be the 4th root of 128. So this is going to be a 2 times the 4th root of 8. So x is going to be 2 times the 4th root of 8 minus 2. The only problem with this is, let's see, there actually isn't a problem. This is in the interval negative 4 to 2. So, success! We've successfully found something. Now, with this comes the question, well, is this telling us anything about the mean value theorem? Because first off, f of x, whoops, how on earth did that end up there? So first off, f of x is not continuous on this entire interval. So that means that the mean value theorem doesn't even apply. However, even though the mean value theorem doesn't apply, this is still going to be something that can happen. It's just that the mean value theorem doesn't guarantee that it exists. Now, let's do something slightly different, still going to be with the mean value theorem. Let's say that we have f of x equals x cubed minus 5x plus 2 on the interval negative 1 to 2. We ask, is there a c in the interval negative 1 to 2 where f prime at c is equal to negative 2? Let's go through and see if this satisfies the conditions for the mean value theorem. So mean value theorem, number 1, we need f of x is continuous. Well, is our function f of x continuous? Yep. So f of x is continuous, so we're good to go. Second one, does f prime of x exist on the interval negative 1 to 2? Well, the derivative of this exists everywhere, so that's perfect. So that means that then there is a c in the interval negative 1 to 2 where f prime at c is equal to f of 2 minus f of negative 1 over 2 minus negative 1. Let's figure out what this is. So f of 2, plugging in 2 gives us 8 minus 10 plus 2, that's a 0. Minus, let's see, we got f of negative 1, that's negative 1 plus 5 plus 2, so that's 6, all over 3, which is negative 2. So is there a c that satisfies this? Yes, by the mean value theorem. Well, the next question that we might ask is, what is it? find it. Find c. So that, in order to find c, we're going to need to take a derivative. So let's look at what is f prime of x. Well, remember, f of x was x cubed minus 5x plus 2. So f prime of x is going to be 3x squared minus 5, and we want this to be equal to negative 2. So that means that 3x squared equals, add 5 to both sides, equals 3, x squared equals 1, x equals plus or minus 1. So which one of these is inside our interval? Well, it turns out negative 1 is right at the edge of our interval, but it's not included in our endpoints. So that means we are going to say that x equals 1 is our c value. Or I guess I can say c equals 1 because that's actually our c value. So c equals 1 in this case. So that's how we would be able to do this problem using the mean value theorem. There's another common test question that we might be asked on our upcoming test to try and figure out how can we use the mean value theorem to help us with this. So it might be something like, prove there is exactly one solution to f of x equals 5x minus 2 cosine of x plus e to the x minus 12 equals 0. Prove there is exactly one solution to this. Now, to prove that there's exactly one solution, we're going to need to use a couple different things. One is we're going to need the intermediate value theorem. Remember this? It's a little bit of a throwback, right? So intermediate value theorem. And then the other one is going to be the mean value theorem. We're going to need to use both of these. So if you don't remember the intermediate value theorem, that says that if f of x is continuous on an interval a to b, then every value between f of a and f of b is reached at least once. So that's what the intermediate value theorem says. And then the mean value theorem says that if f of x is continuous on the interval a to b, f prime of x exists on the open interval a to b, then there is some c where f prime of c equals f of b minus f of a over b minus a with c in the interval a to b. So we need to use both of these in order to prove there's exactly one solution. The way we can do that is the intermediate value theorem. This can be shown to show that there's at least one solution. And the mean value theorem can be used to show that there is no more than one solution. So we are going to use both of these facts in order to prove this problem. So let's go through and do it piece by piece. So let's write down our function one more time. Keep our theorems here so we can see them. So we got f, here, let's just scroll down a little bit. Okay, so we're trying to show that there's exactly one solution. So let's start by using the intermediate value theorem. So intermediate value theorem. We need to find something where the output is bigger than 0 and something where the output is smaller than 0. So let's just pick some really big number. We're going to pick 10 pi. Let's see if that works. So f of 10 pi, well, that's going to be 5 times x, that's going to be 50 pi, minus 2 times cosine of 10 pi. Well, 10 pi, that's 5 times around the circle, so that's going to be at 1. Yeah, 5 full times around the circle, so that means that cosine is going to be 1. That's minus 2 plus e to the 10 pi, and then minus 12. Well, 50 pi, that's about 150, and we are subtracting 14 and adding more. So this is definitely bigger than 0. We now need something that's smaller than 0. Well, let's see what 0 is. F of 0, that's 0 minus 2 plus 1 minus 12. That's definitely less than 0. So that means we have found something bigger than 0 and something smaller than 0. So we could say, thus, by the intermediate value theorem, there is at least one solution between 0 and 10 pi. We don't know where it is, we just know there's at least one solution somewhere there. Now, how can we use the mean value theorem to say that there's not more than one solution? Well, this is where we have to use something in mathematics that's called proof by contradiction. So this is how we would approach this one. So the mean value theorem part, we would say, assume there are two different solutions. So we know there's at least one, so that means there's 1, 2, 3, 4, or more. So if we assume there's two different solutions, that means that our graph is going to be looking something like this, where we have two solutions, maybe more, but we're just going to take two of the solutions. What can we use the mean value theorem with if we know two different solutions? Well, if this function satisfies the conditions, that means that somewhere between these 2 points, there has to be a spot where the slope is 0. So if we can say that there's two different solutions, that means that somewhere between there, if the function satisfies the mean value theorem conditions, there has to be a slope of 0. But if we can show that nowhere is there a slope of 0, that means that we can't have two different solutions. So let's go through those different pieces together a bit more formally. So if there's two different solutions, we are going to say, call them A and B. Okay, so then, by the mean value theorem, since f is continuous and differentiable, we need to specify both of them, and it's continuous and differentiable everywhere, there is some C between A and B where f prime at C equals f of B minus f of A over B minus A. But what did we assume about A and B? They were solutions. So that means that both of them are 0. So we get 0 over B minus A equals 0. So that means we know that somewhere there is a slope of 0. Now, here's where we can get our contradiction. But f prime of x is equal to, so let's go back to our function. Oh, it's way up there. Okay, so let's go through and take the derivative of this. So the derivative of 5x, that's 5. Derivative of negative 2 cosine x, well, that's a positive 2 sine x. Well, plus e to the x. And then derivative of 12, that's 0. So that means that this is our derivative. Is this ever negative? Well, plus 2 sine x, what's the smallest that could ever be? Well, that would be when sine is negative 1. So that means that this is strictly bigger than or equal to 5 minus 2 plus e to the x, which is 3 plus e to the x, which is always positive. It's never equal to 0. So what are we supposed to do about this? We got the derivative is always bigger than 0, but supposedly there's somewhere where the derivative is equal to 0. We just say, this is a contradiction because we have two different things that can't both be true. Therefore, there are not two different solutions. What does this mean? That means there is exactly one solution. That is how we would be able to approach this problem. So, it is a little bit tricky to go through all the different pieces, but remember, Intermediate Value Theorem says that there's at least one solution. Mean Value Theorem shows that there can't be more than one solution. You put it all together, and that's how we would prove that there is exactly one solution. Alright, let's get some practice graphing some functions. Alright, so let's give ourselves a little bit of space so that we have room for graphing. So, let's quickly sketch out some space where we can try and draw this. So we know that we are going to have values going from 0 to 8, so let's at least count up that big. So we got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And then let's go up a few distances this way as well. We don't necessarily need those, but we might need them to get a rough idea of what the different shape is. But all we know are the x values. So now what we do with this to try and get a little better of a graph. So if we're going through the different pieces, let's go through and try and figure out what are some of the things that we can plot. What are we able to do with some of these other pieces, though? Like, the limit as x goes to infinity is negative infinity. What does that mean? That means that way out here, it's going down to negative infinity, and then as x goes to negative infinity, it's also going out to negative infinity. So that just gives us the direction of what's the long-term behavior. Now the next question is, what do we do about the first derivative? How can that help us out? Well, the first derivative tells us if the slope is positive or negative. So, the slope is positive from negative infinity to 1, and from 3 to 6. So that means that from negative infinity to 1, it needs to always be going up. So, we kind of connect the dots. It's increasing there, and then it increases again from 3 to 6. So here's at 3, increases, there's 4, 5, 6. Concavity tell us. Remember, concavity is going to tell us if it's making this sort of shape or if it's making this sort of shape. This is concave up, where the second derivative is positive, and this is concave down, where the second derivative is negative. So it's concave up only from 4 to 6. So from 4 to 6, so let's see, we got 2, here's 4. So it's going to be concave up from 4 to 6. So that means instead of going in the shape we currently have it, it needs to be going in some sort of increasing direction like that. So that has been a little bit of a tweak that we needed to make to our original graph. It needed to be concave up on that region. But then we were told it's concave down everywhere else. So that means that here on this side it needs to be going downwards like this. So we got that, and then it needs to be concave down before we get to 3. So that's going to be something that's concave down kind of like that. And then we also need it concave down after 6. So that's going to be something like that. So we have the concaveness, we have all of that, and then is our function currently continuous on that interval? Yes. So let's go back through and make this much bolder so it's clear what our graph is. It's going up, concave down, comes down, decreases and goes down to infinity. And then it does the same thing on the other side, where it goes, has a concavity switch. We're going to make that one solid, this one open, and then it's going to go concave down like that. So this dark blue graph is going to be what our graph of f of x would be. Is this the only one? No, but this is a valid one that we can use. Let's do another one, but this time I'm going to give you the function and we are going to have to graph it. So let's say that we are trying to graph f of x is equal to 18x squared minus 4 divided by x to the 4th plus 9. If we were given this and told to graph it on a test, how would we do that? Especially if we weren't given a graphing calculator. How are we going to be able to do that? Go ahead, pause the video, and try and do your best to graph this function. Okay, so the way that I would tackle this is I would try and figure out as much different pieces of information as I could. So one thing is, I would like to know what is f of 0 and f of x equals 0 where. We want to know those things so that when we are going through and plotting them, we can be able to say, oh, f of 0 is this point, and then we know it's equal to 0 here, here, and here. That gives us a good starting point. But right now, we don't have those, so we need to go through and find them. So f of 0, let's evaluate what that is. That's going to be 18 times 0 minus 4 divided by 9. So this is 18 times 4, that is 72, divided by 9. So negative 72 over 9, this is negative 8. That means down here, 1, 2, 3, 4, 5, 6, 7, 8. It passes through that point. So that is one piece that we can use to help us figure out this graph. The next one is we need to solve for where is f of x equal to 0. Well, f of x is equal to 0 when this fraction is 0, and the fraction is only 0 when the top is going to be 0. So that means we can say that 18, whoa, that's huge. Let's make that smaller again. So that is going to happen when 18 x squared minus 4 equals 0, or when x squared minus 4 is equal to 0, when x squared is 4, or when x is equal to plus or minus 2. So that means that both of these spots, 1, 2, negative 1, negative 2, it's going to be equal to 0. So we have currently gotten two different pieces of information that are able to help us get a general idea of what the graph is. So what are some other things that we could be able to use to help us figure this out? Well, another one might be, where is this function continuous? So let's go and figure that out. Where is f of x continuous? And along with this is going to be finding anywhere where we might have an asymptote. So if we can find any asymptotes, we add those to our graph, and that just gives us a little bit more information. Well, f of x is continuous. We have polynomial divided by a polynomial. This is going to be continuous when x to the 4th plus 9 is not equal to 0. Well, x to the 4th, the smallest that can ever be is 0, and then plus 9 means that this is never going to be 0. So this is going to be continuous everywhere. So that tells us quite a bit, actually. It means we're not going to have any jumps, we're not going to have any holes, we're not going to have any vertical asymptotes. But what about horizontal asymptotes? Where do we have some horizontal asymptotes? Do we have any of those? Well, remember, the way we find horizontal asymptotes are we look at the limit as x goes to plus or minus infinity of f of x and see what those are equal to. Well, in this case, if we look at that, the top is an x squared and the bottom is an x to the fourth. So as x goes to infinity, the bottom is going to grow much, much faster, which means that this entire thing is going to basically just approach 0. So our horizontal asymptotes mean it's going to be pretty much 0 on either side. The only question is it going to be positive or negative 0? Or approaching 0 from the positive direction or from the negative direction? Well, as x is really, really big, the top is going to be positive, and the bottom's positive, so it's going to be approaching from just above the axis. So that tells us a little bit more information. What can we do now, though? We don't really know how does it connect. So like, does it connect like this? How is it going to connect? Well, let's try and figure out a little bit more information. Some other things that we might want to check are there any symmetries? Is this function symmetric? So, is f of x even? Is it odd? Is it neither? These are things that we would need to check to figure out, is this going to be symmetric or is it going to not be symmetric? Well, how do we check if something is even? Well, remember, even, that is where f of negative x equals f of x. Odd is where f of negative x equals negative f of x. And then neither is when neither of those are true. So let's test each of these. Let's look at f of negative x. Well, that's going to be 18 times negative x squared minus 4 over negative x to the fourth plus 9. Well, negative x squared, that's just x squared, so we get 18 x squared minus 4 over negative x to the fourth. Well, that's just x to the fourth. This is the same thing as f of x. So this means that f of x is actually an even function. So what does that mean? Well, that means that if something does this on this side, it's going to have to do the same thing on the other side. And if this has this weird shape there, on the other side it's going to have the same weird shape. So that means that we know that this function's even, so it's going to be symmetric across the y-axis. So that tells us some information too. Now what else can we do? Well, we're in a calculus class, so that means we're probably going to need to take some derivatives. So what would the derivatives tell us? Well, the first derivative tells us if the slope is positive or negative, and then the second derivative would tell us the concavity. So let's go through and do some of those things now. So, to do that, we're going to need to know what is f prime of x. Well, f prime of x, we're going to need to take a derivative. How do we take the derivative of this function? Well, you guessed it. It's going to be the quotient rule. So we got low d high, x to the fourth plus 9, times the derivative of the top. 18 can stick around, times the derivative of x squared minus 4, that's a 2x. So low d high minus high d low, all over the bottom squared. Great. What are we supposed to do with this? Well, the first derivative can tell us where is the slope 0, and it can also tell us where are we going to be able to have positive slope and negative slope. So let's solve for where is f prime of x equal to 0. Well, again, the bottom, that's not going to play any role, so we only have to look to see where is the top equal to 0. So that is going to be, we got x to the fourth plus 9 times 36x minus let's see, we got minus 18 times 4, that's 72, so minus 72x cubed times x squared minus 4. Distributing all of that through gives us 36x to the 5th. 9 times 36, that's 9 times 9 times 4. So that's 81 times 4, so that's 324 x. Then we have a minus 72x to the 5th. And then a plus 4 times 72. Let's see, 4 times 72, that is 280 plus 8, so plus 288 x cubed. So doing a little bit of simplifying here, let's see, everything actually is divisible by 9. So let's see, so 36x to the 5th minus 72x to the 5th, that's negative 36x to the 5th. Let's see, plus 288 x cubed plus 324x. So we can pull a 36x out from everything. So we got, oh, actually, I don't know if we can pull a 36 out. We can at least pull 18 out. So 18x, we have a minus 2x to the 4. 288 divided by 18, let's see what that is. 288 over 18, that's 16. So plus 16x squared, and then 324 divided by 18, that's 18. Oops. So we could have actually pulled out another negative 2, so let's do that right now. So this is negative 36x times x to the 4th minus 8x squared plus or minus 9. And now we need to factor that. Well, factoring that might be a little bit tricky unless we recognize that this is x squared minus 8x squared minus 9. So then this will actually factor out pretty nicely. If we factor this, we get negative 36x times, how would we factor just x squared minus 8x minus 9? Well, that'd be x minus 9 times x plus 1. Replace those x's with x squareds, and that's exactly how this factors. X squared minus 9, x squared plus 1. And now where is this equal to 0? Well, it's equal to 0 wherever this, or this is equal to 0. So that means we get a 0 at x equals 0, x equals plus or minus 3, and then we don't get any from x squared plus 1, because the solutions to that would be the square root of negative 1, which is not a real number. So that means that we have a slope of 0 at 0 and plus or minus 3. So that means the slope right here is 0, and then the slope on this side at 3 is going to be 0, and at negative 3 it's going to be 0. Now, why did I draw those two at the same height? Well, it's because this is an even function, remember? So that means that we need to have it be symmetric across that axis. So that's why those are both going to be symmetric. So now that we have our critical points, so let's write those down. So we have critical points, x equals negative 3, 0, and 3. We can now go and figure out where's the slope positive and negative. And the way that we would do that is we are going to be looking at the second derivative on either side of those critical points. So let's go through and do those one at a time. So if we draw our little line, we have 0, we have 3, we have negative 3. We need to know what is the second derivative, or the first derivative on either side of those points. So our second derivative, let's evaluate it at some different points. So let's look at negative 4, negative 1, 1, and 4. So f double prime at negative 4, not f double prime, just f prime. Let's go through and look to see what is f prime at 4. f prime at negative 4. Well, this is going to be negative 4 to the 4th plus 9, so that's going to be a positive. Let's see, negative 4 there, so that's a negative. We'll see if we can do it without having to do anything else to see if we can figure out the sign directly. If not, we're going to have to go through and actually evaluate the numbers. We have minus 18 times negative 4 to the... So let's see, negative 4 squared, that's 16 minus 4, so that's going to be a positive. And then that's a negative. So negative plus positive, we don't know that sign. So we're going to actually have to go through and compute this number. Sometimes we're lucky and we don't actually have to find the number, but this time we do. So let's see what we get. So negative 4 to the 4th, that's 16 squared plus 9 times 18 times negative 8. We have minus 18 times 16 minus 4, so that's 12, times 4 times negative 4 cubed. So we'll figure out what that is in a sec. And then the bottom's positive, so let's just look to see what these are. So let's see, so 16 squared, that's 256. 256 plus 9, that's 265. Times negative 18 times 8. What is that? So 18 times 8, that's 144, so that's times negative 144. But then we add to that 18 times 12. Let's see, 18 times 12, that is 216 times 4 to the 4th. So that's another 256. So it's pretty clear that this number is going to be bigger. So this is going to be positive. So that means that from negative infinity to negative 3, the slope is positive, which is about what we were expecting, because we know it's 0 and then it needs to be above the axis, so the slope should be positive there. Now if we plug in negative 1, we would hope that the slope is going to be negative to be able to connect our dots. So let's go through and test that. Let's look at what is f prime at negative 1. Well, that's going to be a lot easier to calculate. So let's see, negative 1 to the 4th, that's 1 plus 9, that's 10, times negative 36 minus 18 times 1 minus 4, that's negative 3, times negative 4, all over a positive. So let's see, we got negative 360 plus, or minus 12 times 18. This is definitely going to be negative. So the slope is going to be decreasing. And then we know it's even, so we actually don't have to test the other numbers. We know it's going to have to be reflective, so it's going to have to go like this. So now we just have to fill in what's the specific shape, and we're going to be doing that using, you guessed it, the second derivative. So let's go through and find the second derivative of this. Now, is this going to be pretty? Probably not. Second derivatives rarely are pretty, but we're going to have to do it anyway. So let's actually simplify f prime of x a little bit beforehand. Alright, so after combining a few terms, we can see that the first derivative is going to be the following. We get negative 36 times x to the 5th minus 8x cubed minus 9x, which we actually had done a little bit ago, over x to the 4th plus 9 squared. And now we need to take the second derivative. So, not very pretty. Second derivative of x, going to do the quotient rule again. So we got low d high, so x to the 4th plus 9 squared times the derivative of the top, stick a negative out front, times 36, derivative of that inside, 5x to the 4th minus 24x squared minus 9, low d high, minus high d low, so that's a plus 36 times x to the 5th minus 8x cubed minus 9x times the derivative of the bottom times 2 x to the 4th plus 9 times 4x cubed all over the bottom squared. X to the 4th plus 9 now to the 4th. Now fortunately, all we really care about are the points of inflection and where it's positive. So we don't actually need to find very much except for the top. We need to solve for where the top is 0, which is not very pretty, but we know it's going to happen somewhere. So let's go through and actually just churn this out. So, told you graphing these very rarely is pretty by hand. So let's see what we got. Well, we have an x to the 4th plus 9 squared in this term, so right here, and we have an x to the 4th plus 9 here, so we can actually simplify this a little bit before we do anything. We can cancel that with one of these and one of these down here. So that makes it a little bit easier. Is there anything else that can cancel? We'll see, there's a 36 in everything, so let's just pull that out. So we got 36 times, we got a negative 5x to the 4th. Oh, whoops, we have the x to the 4th plus 9 still. X to the 4th plus 9 times 5x to the 4th minus 24x squared minus 9. We pulled that 36 out. We have plus 4x cubed times 2 makes that 8x cubed times x to the 5th minus 8x cubed minus 9x. So that's the top all over x to the 4th plus 9 cubed. Okay, let's go through and see if we can combine some terms. It's not going to be very pretty, but we're going to have to do it. So we got 36 over the x to the 4th plus 9 cubed. That's never 0, so let's leave that be for a moment. Then let's distribute all of these terms through. So we got all of those that we got to deal with. So that's a negative, come on, there's the negative 5x to the 8 plus 24x to the 6 plus 9x to the 4. And we have a minus 45x to the 4th plus 24 times 9. What is that? 24 times 9, that is 216. So let's see, we got a plus 216x squared and a plus 81. Yikes, this is getting ugly. But then we have a plus 8x to the 8 minus 64x to the 6 minus 72x to the 4. So we have all of that. And now we need to solve for where is this equal to 0. Great. Isn't this just absolutely what we want to be doing, reviewing for a test? This is our favorite sort of thing, right? Yeah, I didn't think so. So let's see, we got 36 x to the 4th plus 9 cubed times negative 5 plus 8, that becomes a 3x to the 8. So we've gotten that and that taken care of. 24 minus 64, so that's a minus 40 x to the 6. So that's that one and that one taken care of. 9 minus 45, so that's a negative 36 minus 72, that's minus 96, no. 36 minus 72, that's minus 108. X to the 4th. Then we have a plus 216 x squared plus 81. That takes care of all of these pieces. and we want this to be equal to 0. So that is where something in here is equal to 0. So let's figure out where those are. I'm not going to try and do this by hand. I am instead going to use a calculator to figure it out. Because this is not something that you would be able to do without a calculator, so this is not an expectation of being able to find them. However, trying to do this and the ones on your test would be ones that you would be able to do by hand. So give me a moment and I will figure out where is that going to be the case. Alright, so this one has a few different spots where we have some solutions, and they are at approximately negative 3.92, negative 1.27, positive 1.27, and positive 3.92. So those are where we have approximate zeros. And so then we just need to find what's the second derivative on either side of these. And if we were to go through and put these on a number line, so we got negative 1.27, negative 3.92, 1.27, 3.92. There's some pretty easy numbers to plug in. We could plug in 0, negative 2, negative 4, 2, and 4. And when we go through and do that, we're going to find that as positive here, negative here, and then positive here. So what can we do with this information? Well, now that we have that, we can take that and apply that up here. So we know that there is going to be a point about here and about here where it's going to change concavity, and then another one about here and about here, because that's at, let's see, 3, oh, it's almost at 4. So it's actually going to be about there and about there, so just before 4. So those are going to be the spots where it changes concavity, and we know that the concavity is concave up in certain spots. So it's concave up. So remember, second derivative goes positive, negative, positive, negative, positive. So if we were to want to do that, if it's concave up where it's positive, well, that's going to be this shape here, and then it's going to be concave up after this, so it'll be something like that, something like that. But then it's concave down on the other sides, so it'll be like this, there, and concave down, there. So that means that this is going to be our rough graph of what the graph would be. So that's how we would go through graphing something like this. Is it a little bit complicated? Yeah, it's pretty complicated. But we have all the tools to do it. The only spot where we got really hung up and weren't able to do it by hand was down here when we had this really big polynomial we needed to find the zeros of, which is not something that you would be expected to have to do on this test. But doing things similar to that and being able to solve it if it was a simpler problem are things that you would be expected to be able to do. I hope you enjoyed this video and that it was helpful for you. Please check out some of my other videos, and please like and subscribe if you have not already so I can continue to make these sorts of videos. Have a great day and good luck with the rest of your math.